Hello everyone. Today I am here to discuss the Heisenberg uncertainty principle and de Broglie's relationship. After studying this lecture, you shall be able to know the concept of Heisenberg uncertainty principle, understand the de Broglie's relationship, solve problem based on the Heisenberg uncertainty principle and de Broglie's equation. In atomic structure, first we discussed the basic terminology, that is, what is atomic number? The atomic number of a chemical element is the number of protons in the nucleus of an atom of the element. It is represented by the symbol Z. What is atomic mass or mass number? It is the sum of the number of the protons and neutrons present in the nucleus of an atom. It is represented by the symbol A. First, we discuss Heisenberg's uncertainty principle. According to this principle, it is impossible to determine simultaneously both the position and velocity or momentum of a small moving particle like electron. In other words, the uncertainty principle says that we cannot measure the position, that is x, and the momentum, that is p, of a particle with absolute precision. The more accurately we know one of these values, the less accurately we know the other. Means, if the position is determined with accuracy or precision, the momentum becomes less accurately known or uncertain. The uncertainty principle, called Heisenberg uncertainty principle or indeterminacy principle. This statement articulated in 1927 by the German physicist Werner Heisenberg that the position and the velocity of an object cannot both be measured exactly at the same time. According to the Heisenberg uncertainty rule, it is not possible to know exactly both the position and the momentum of an electron. Thus, the certainty of the determination of one property leads to uncertainty of determination of the other. Delta x stands for the uncertainty in the measurement of position and delta p stands for the uncertainty of determination of momentum, are related by the Heisenberg's relationship as delta x multiplied by delta p is greater than equals to h upon 4 pi, where h is the Planck's constant. If delta x is very small, that is, the position of the electron is known more or exactly less, means delta p would be large, that is, uncertainty of the momentum will be large or vice versa. So, delta x multiplied by delta p is greater than equals to h upon 2 pi, where delta p is equals to m multiplied by delta v. So, we put the value of delta p. So, the equation is delta x multiplied by h delta v is greater than equals to h upon 2 pi. Now, we will solve some numerical which is based on Heisenberg's uncertainty principle. So the question is, the uncertainty in the position of a moving bullet of mass 10 gram is 10 to the power 5 meter. Calculate the uncertainty in its velocity. In this numerical, we have a mass that is 10 grams and the change in position, that is 10 raised to power minus 5 meter, and we calculate change in velocity. So we apply a formula of Heisenberg uncertainty principle, that is delta x multiplied by delta p is equals to h upon 4 pi, where delta p is equals to m multiplied by delta v. So the formula is delta x multiplied by m multiplied by delta v is equals to h upon 4 pi. Now we calculate this velocity. So the formula is delta v is equals to h upon 4 pi m delta x, where h is the Planck's constant whose value is 6.626 multiplied by 10 raised to power minus 34 grams meter square per second, where m, that is the mass, which is 10 grams. So we gram convert into kilogram. So this is 10 raised to power minus 2 kilogram. Change in position is 10 raised to power minus 5. So apply all the values in this formula and get the answer, that is 5.27 multiplied by 10 raised to power minus 28 meter volt. Next question is uncertainty in the position of a minute particle of mass 25 grams in space is 10 raised to power minus 5 meter. The uncertainty in its velocity in meter second inverse is, so we calculate the velocity. We apply the formula h upon 2 pi m multiplied by delta x. Put all the values and calculate delta V. Now we discuss the de Broglie's theory. In 1924, a French physicist, Louis de Broglie, advanced a complementary hypothesis for material particles. According to it, the dual character, that is, the wave and particle, may not be confined to radiation alone but should be extended to the matter as well. In other words, matter also possessed particle as well as wave character. This gave the birth to the wave mechanical theory of matter. This theory postulates that electrons, protons and even atom, when in the motion, possessed wave properties and could also be associated with other characteristics of the wave such as wavelength, wave amplitude and frequency. The new quantum mechanics, which takes into account the particulate and wave nature of the particle, is termed as wave mechanics. De Broglie have arrived at his hypothesis with the help of Planck's quantum theory and Einstein's theory of relativity. He derived a relationship between magnitude of a wavelength associated with the mass m of a moving body and its velocity. According to the Planck's, the photon energy E is given by the equation H is equals to h nu, that is equation number 1, where h is the Planck's constant, V is the frequency of the radiation. By applying the Einstein mass-energy relationship, the energy associated with the photon of mass m is given as E is equals to mc square. This is equation number 2, where c is the velocity of the radiation. So, if we compare equation number 1 and equation number 2, then we get a equation, that is mc square is equals to h nu, where nu is equals to h upon c lambda, or mc is equals to h lambda. This is equation number 3. Mass into velocity is equals to h upon wavelength. Momentum, that is p, which is equals to h upon wavelength, or we can say momentum is directly proportional to 1 upon wavelength. So this equation third is called de Broglie's equation and may be put in word as the momentum of a particle in motion is inversely proportional to the wavelength, Planck's constant h being the constant of proportionality. Now we solve some numericals which is based on the de Broglie's theory. First question, calculate the wavelength in nanometer associated with the proton moving at a velocity 1 multiplied by 10 to the power 3 meter per second, where mass of the proton is equals to 1.67 into 10 to the power minus 27 kilograms and h having a value 6.63 into 10 to the power minus 34 joule second. Now we apply a formula, that is lambda is equals to h upon mv, where we know the value of h, put the value and get the answer, that is 0.4 nanometer. Next question, calculate the wavelength of a golf ball weighing 200 grams and moving with a speed of 10 meter per hour. Apply a formula, lambda is equals to h upon mu, where we put the values of h, m and u and get the answer, that is 6.626 multiplied by 10 to the power minus 30 meter per hour. Next, calculate the de Broglie's wavelength of an electron moving with velocity of 5 into 10 to the power 5 meter per second. Again, we apply a formula, lambda is equals to h upon mv, put the values and get the answer, that is 1.46 into 10 to the power minus 9 meter. The last question, what is the momentum of a photon with a de Broglie's wavelength of 4.6 meter? Estimate h as 6.63 into 10 to the power minus 34 joule second. So for this numerical we apply a formula, momentum is equals to h upon lambda, where we know the value of lambda, that is 4.6 meter. Apply all the values in this formula and get the answer. Now we have some practice question, that is define the term Heisenberg uncertainty principle. Write the short notes on de Broglie's relationship and we solve some numerical based on Heisenberg and de Broglie's relationship. These are the references. Thank you.